All right, today let's look at dynamic relaxation inside LS-Dyna. I have agenda here today. We're gonna do an overview for DR, looking at the different type of DR, what it does, what are the nuances. It's a pretty easy thing to use, but there are also some interesting nuances, which is why I decided to make a video about it. It's a topic I think, I would have thought I knew 100% of, but it turns out I only know like 80%. So the research helped me figure out to close the knowledge gap for the other 20%. Once we look at the overview, I prepared three simple example to look at a bolt preload, a rotating body, and a dummy model in which I intentionally use DR to close the clearances in the geometry, so that you have correct contact being established before the transient analysis. So three very interesting and very useful applications for dynamic relaxation. And this is a preload system that's used almost everywhere. It's a very useful and also very easy to implement feature for LS-Dyna. Okay, quick overview. LS-Dyna really, dynamic relaxation really is used to sort of generate a preload or generate or damp out a system before the full transient analysis. So think of this as the pre-stress condition that you're adding before you do the full transient analysis, right? And this is done inside what they call a pseudo end time. Basically, it's essentially the time domain that's before the full transient analysis. So you have a separate part of the analysis that's not really doing a full analysis, but except it's trying to damp down the nodal velocity and trying to establish a pre-stress condition in the model. Is essentially what DR is used for. Dynamic relaxation, as a result, right, it essentially damps out your nodal velocity. So any ring in the system, depends on the dynamic relaxation factor value you use, can basically give you a much more stable pre-stress conditions. Um, the way dynamic relaxation works is that it's essentially checking for what they call a distortion kinetic energy. This is basically like the KE of the system that is evaluating, or the body that is evaluating, and he's going to compare to the peak distortion KE in the system. So for example, if you have a rigid body motion, right, the rigid body motion will have exactly the same distortion KE as its peak distortion KE because there's nothing stopping the body. But what the system is going to do is that it's going to keep checking for that convergence tolerance. When that rigid body hits something, the velocity stops, therefore KE drops. At that point, the current KE is going to be a lot lower than the peak KE, and that's when you reach convergence. So what I just described, as I will sort of iterate again in the next step, is that this is basically how they check for how the dynamic relaxation can be used to close initial gaps. For pre-stress, it's the same condition. When you apply a pre-stress in the transient domain, right, you're gonna have this ring in the system. So what DR is going to try to do is try to damp out that initial ring in the system before it let you finish up before you go to the full transient analysis. DR can be implicit or explicit. The decision is exactly the same as you consider for explicit versus implicit analysis. Um, and it can be activated by looking at essentially different loads and different pressures and different boundary conditions. And for those, usually there's a defined curve that's attached to them, and then the defined curve has a parameter called SIDR. Sending it to 1 or 2 will basically include the dynamic relaxation in the system. So it's very useful. Like I said, I'll show the example, right? You can do pole preload, you can do pre-stress due to inertia, you can close gaps, you can also damp out the systems. So there's no ringing in the system at the beginning of the transient analysis, where if you wanted to go to the implicit analysis, it's also very, very useful. Okay, so dynamic relaxation basically can be activated inside a workbench. I apologize, I'm gonna move this a little bit. There we go. Dynamic relaxation can basically be activated inside workbench relatively easily. You basically set to a explicit type of DR, and then you can say your pseudo end time, and then the tolerance right here is basically this tolerance value, right? And then the relaxation factor right here. The lower this number is, the more damping you're adding to the system, but sometimes that can really slow down the convergence. So it's a balance between how quickly you wanna kill the nodal velocity. And I'll demonstrate in one of the example in a bit, so we can get a like a visual understanding of how it works. All right, so like I mentioned earlier, DR can be implicit or explicit, right? So the ID flag parameter here basically has all these options, which is going to allow you to activate implicitly or explicitly. Basically, you use one to generate dynamic relaxation, and then you use 5 or 6 to do it implicitly. The other ones, I have never really used them. Uh, uh, but they're basically just for, instead of checking the whole system, you can check multiple bodies, but usually you just check the whole system. That's a pretty good way to look at it. You don't want to really check just a few bodies as far as I can imagine. And then, dynamic relaxation implicitly, if you set this, for example, if you set this keyword here, dynamic control here to implicit, right? If you do that to implicit, what it would do is that you will actually write out these control cards for the implicit analysis with a dash dyn at the end. This is a default control card that the workbench writes out, which is really silly because they just set everything to 0, which is not what you wanted to do. So the way I've generated is I've created a template based on my implicit control card template, which is what I'm going to use to run implicit dynamic relaxations. I think it's a much better way to handle it. It has a this is a very similar to what the DR card, the dynamic relaxation. I'm sure the implicit card I've always used, but in this case, it's going to be specifically for implicit dynamic relaxations. Okay, so once we have all of these, this is the basic overview. Remember, it checks for the KE, the current KE versus the PKE, and then it's gonna converge when it reaches when the ring stops. You can set this number to be way lower than 1 to -3 to really prevent a lot of the ring in the system. And then you can also use this to close gaps. Okay, let's look at a couple examples together. So this example right here is a bolt preload example, right? Pretty simple. So what I have here is you have these bolts, bolt preload that's going to be applied across the system. So dynamic relaxation here, if you do insert bolt preload, you get these right here. These right here are specifically for dynamic relaxations, and it's going to ask you for a bolt preload stress. So interestingly, this is different from ANSYS Mechanical, where you're adding a force value. In this case, they're asking you directly to input a stress value, which is very convenient. Now you can also do this during the transient analysis. So these 4 right here will be actually account for the transient analysis, right? Everything else is basically just a fixed support on there, and then that's pretty much it. There's not a lot to it. I won't go into the little contact detail, but basically you can sort of imagine you're just bolting things together. The bolts are tied to the nuts, and everything else is frictional contact. And if you were to do something like this, what you can sort of see is that I'll just show you an example results. Um, yeah, so let's look at this one. So I forgot I should mention before I go there. So the dynamic relaxation require a different database card than D3plot. D3plot is for the full transient analysis. This D3DRRF, this one right here, D3DRF, it's hard to say. Basically, it's for the dynamic relaxation database card. The dynamic relaxation database card writes out this D3 drift card. I don't know why they name it that way. It's so hard to say. But basically, that's DR database. DR database gives you the results inside the dynamic relaxation by allowing you to sort of see what's happening inside the dynamic relaxation phase, right? And then this is very important to know. And then what we can sort of see is that you don't see anything right now because the bolt is hidden. If I do that and reverse it, you should be able to see it. And then if we can just move all the way to the end. Um, yeah, so you can sort of see there is a dynamic there's a pre-stress that's added in the bolts. And if you want to take this to the full transient analysis, and then you can sort of see the same thing in this case. If I reverse it, then you can sort of see the stress on the bolts, which is going to be a little bit different, right? Because this is the beginning point, and then it's gonna basically load it. The reason the stress here looks a little bit different is because in dynamic relaxation you have a cross-section area that you're applying the load from, which is why it looks like this. But in this case, this is the actual bolt stress in the full transient analysis. This is where the ring of the system gets removed and you're adding that preload and then kill the ring of the system. That's all you're doing. Okay, and then this is basically the first example. So if you want to look at the whole example, you get these relatively clean. Oops, sorry. Okay, you get these relatively clean. Set to 450. You get these both preloads applied to the analysis, and you can sort of see the beginning and the end is the same because I'm applying a 900 sort of megapascal stress across the whole thing without any ramping. This is how you know at the very beginning at t equal to 0, this is the pre-stress that you're looking at. Okay, and that's in essence what it is. And then one of the interesting things to think about is that if I look at here, I believe I can actually show. Okay, let's look at the next example. The next example is let's look at a rotating body. This rotating body basically has a look like this, right? So I have a rotating body that look like this, and then these are no merged, and then I'm gonna apply a rotational velocity, and I'm gonna apply it for during dynamic relaxations, right? So that I can see this thing rotating. And then what you see when you look at analysis like this is that it's actually going to include. Actually, let me show you this. Let's look at the rotations, and then if I just look at DRF, right, and then this is the dynamic relaxation database file, and if I just show the what means the stress. Okay, this is the stress due to the rotating body. This is all inertial stress, right? As the body rotates, inertia is going to cause some stress on the rotating body. And then if I take it to the full transient, you get a similar situation to the previous example. And I didn't have any additional load, so you get basically the same stress, relatively speaking, the same stress across. This one just damps out the system, and this one gives you the full stress as a function of the transient analysis. This one right here just initialize the stress, and then make sure the ring in the system is 0, and this one you have the full stress that you can actually look at. Okay. And this is how you generate the dynamic relaxations in this card. So in this example, all I'm doing here is I have my dynamic relaxation, I have my rotational velocity, it's assigned to the general preload, and then I have some termination time, and dr is initiated with a pseudo end time, and that allows that pre-stress to be induced on the structure, basically. Okay. All right, a couple more useful examples to take a look at it. So another example that's very, very useful to think about is, say for example, you have a plate, right? You have a plate and a slot that receives a plate. Initially, there is no contact, so I have a contact pair here between the one side surface of the plate and the other side, which has essentially a gap. Now, as you can imagine, if you solve this model, if I were to apply a pressure on this thing, eventually this contact is going to hit. But initially, there is no contact, which means you have rigid body motion in the system. And that will cause a problem in a larger structure, in which if you have rigid body motion, you're going to have these small pivots, and that's going to cause a problem in the implicit analysis. So what we can do is use dynamic relaxation to essentially causes the plate to hit the slot around that contact surface before the initialization of the transient analysis. Right, and the way we do that is, let's go ahead and start a new session. Let's go ahead and look at this session. I'm gonna look at the session where I have a large gap. Actually, I'm gonna have with a gap kill the motion here. So you can sort of see in this example, right? In this example, I have a very, very small gap. And you can sort of see that the end of dynamic relaxation is going to basically close this gap. And that's what DR did, is that it's actually going to look at the distortion KE versus the peak distortion KE. When the red plate hits the slot, the KE is going to go down. And that's when you have convergence of the dynamic relaxation. So it's a very good way to kill any rigid body motion in the system. So if I were to show you the kill motion, and I want to show you this file here. And what you can sort of see is that you have the start time, and every 250 cycle is going to calculate a DR, and you see how distortion energy just goes down, and the max distortion energy does not go down. And then once it goes down to a small enough level, you have convergence factor, which is below 1 to -3. And in this example, I believe I will be able to probe. Actually, I need to turn on the full transient analysis before I can probe. Sorry about that. That's what I forgot in my previous example. So in this case, you can see how in the t equal to 0, right, the plate is not in full contact with the slot. Now, if I were to probe stress, you can sort of see, you can see that you said ringing right there. That ringing still exists. But at t equal to 0, we could have killed that ringing by setting the scaling factor to a number way lower than that. In this case, we didn't. That's why you still see some ringing in the system. Okay, now let's look at another example. Let's look at another example in which you see how much this is exactly the same problem as the previous example, except I intentionally made the gap extremely large. Okay, so the question is, what do you think happens when that's the case? Now, let's go ahead and look at the example I already prepared. There's not, I didn't show you the step because it's really simple, right? The step doesn't matter. What I wanted to make sure to illustrate is how important how DR works and how changing different parameters. So in this case, if I were just to probe the stress, right? So you can sort of see it took a long time for the plate to hit the surface because the gap became larger. And then if I were to look at the input file that I generated here, right? So actually, let's go to do gap -gap 07. So in this case, if I show you my control dynamic relaxation card, you see how my scaling factor is 0.95, which means in this specific example, if I were to put this number as 0.95, that's what you're seeing. Now, the default is 0.995. That's default. The 0.95 is what I added, what I changed. Now, the question is, what do you think happens if I use the default? You see how much slower this goes, right? Because it's the scaling factor, the dynamic relaxation factor is what scales the velocity. So if I were to rerun analysis with a much lower, where is my results? There we go. That's it. So this one right here is where I am looking at the. Oh, whoops, sorry. So you can see in this case, you see how much faster it is. This is 0. This one right here is with 0.995 as the default relaxation factor. This one right here is with a 0.95 relaxation factor. Just by changing a small fraction of the relaxation factor, I drastically slow down the analysis, right? Or the dynamic relaxation speed. But what happens also is that if you reduce the relaxation factor, you're gonna damp out a lot less. You're gonna make the rigid body motion damp out a lot slower, and it's gonna take longer. But the benefit of this is that depends on the natural frequency of interest. Sometimes you need to reduce the damping factor to get the correct amount, so you don't over damp the system. And that's something that we're studying. Usually, you can play around with this number depending on what your initial. What you don't want is the initial in the start of the transient analysis, you have some ring in the system. So to demonstrate that, I can sort of show you if I don't use large gap 7, if I use large gap, and if I look at this one right here, and then if I were to show you, you see how there is still ring in the system. You see that ring in the system that exists. Because I didn't damp it out during dynamic relaxation, the ring still exists, right? And if I were to probe hopefully it's not gonna crash on me. It might crash on me. Yeah, okay. Let's just reopen it. I'm gonna show you real quick the ring in the system that happens. D3 plot. Okay. Well, this is actually not the best example, but let's use the other one. Let's use a large gap. D3 plot. And if I were to say, for example, probe, I'm gonna probe x velocity on that node, and I'm just gonna plot it. You see how the ring that exists in the system, right? Now I can reduce this value by making the dynamic relaxation convergence factor a lot lower, and that will reduce this ring of the system. I'm probably not going to be able to demonstrate it here, but it will be. So for example, instead of doing 1 to -3, if I do 1 to -7, right, and I use 0.995, I'm just going to solve it. Let's see what happens. I'm going to do it live. DC full review, gap 1 to -7, and I want to do very low convergence gap, and then I'm gonna solve that. I'll just solve it, and then talk the rest of the way. Might take a while though because the divergence factor is so much lower, but we'll see. It's a very small model, so maybe it will solve before I finish the video, and I can take a look at it. Sort of see it's just going right. Right now, what it's doing is this is a ratio of 1, which means it's just going to rigid body motion, and then over time it's gonna keep going until it hits the plate. Once it hits the plate, it's gonna die down until this number becomes lower than 1 to -7, and once that's the case, it's going to converge. And then I can show this. So as you can see, as soon as the dynamic relaxation goes to finish, you can see once it goes below 1 to -7, it's gonna converge. Once it converges, it's gonna keep going until you finish the transient analysis. And then once you have that, what we can do is look into all those parameters and let's do some post processing, right? So let's do this one. Let's do D3 plot. So this is with 1 to -7 dynamic relaxation. So you can sort of see in this case, if I were to probe the stress, you can sort of see the ringing will be much lower. You see there's almost no ringing left. And then what you do here is you do nodal and do y velocity, x velocity. And you can sort of see this is a very, very low curve, right? Now if I were to do the same thing, and if I were to go back to the original one with a much smaller much larger convergence factor, and what you have here is same thing, but you can sort of see there's a lot of ring in there. You see that ring is almost noticeable, right? And if I were to do nodal velocity on here, so you can see how this goes up to 40 to 60 millimeter per second, and then in the same analysis on previously, if I were to go here, it's not very easy to. I should put them in the same plot so I can compare them. You see, this is -0.6 e to -3, right? So this is a 0.6 meter per second, a millimeter per second, and this one right here is almost 50 millimeter per second, right? That's the difference between 1 to -3 and 1 to -7, right? So see how much the damping was reduced by the system, and that's really what dynamic relaxation does, is that it closes out the nodal velocity, damp out the system, so you have the proper amount of lack of ringing in the system before you start the full transient analysis. And that's the overview of dynamic relaxation in great detail. It can be used to close the gap. It can be used to generate initial stress. It can be used to damp out the ringing of the system. Very, very useful capability within LS-Dyna. All right, thank you very much.